Hi everyone. I hope you had a nice weekend. I don't know if you've seen any eggs, but if you could just look around at your feet to see if there are any because they have candy in them, and I don't want Bean to eat them, but you should eat them. So, yeah, I hope you had an enjoyable weekend. On Friday, we had just written down the definition of a ring homomorphism. So just to recall this quickly before we go into the properties of ring homomorphisms. A ring homomorphism, phi from a ring R to a ring S, is a function such that that function preserves the addition operation in your ring, and it also preserves the multiplication operation in your ring. And if your function phi is bijective, it is called an isomorphism. Okay, so these are ring homomorphisms. So I'm going to give you a few minutes to think of some maps between rings that might be examples of ring homomorphisms, and then we'll discuss those. So yeah, go ahead and take a few minutes to think about and discuss what some examples of these might be. Okay, I'm gonna go ahead and give you two examples that I had written down. So we can make one from the integers to the integers mod n by just taking any integer k and sending it to k mod n. Okay, so this is an example of a ring homomorphism. And another one that I wanted to show you is from the ring of polynomials in X with real coefficients to the real numbers given by, we'll say we take phi of a polynomial f of x and send that to f of 1. Okay, so if you like, you can check that these two maps are examples of ring homomorphisms. So now I'm going to give you, just as we had for group homomorphisms and group isomorphisms, I'm going to give you a long list of properties about ring homomorphisms, and I don't think any of these are going to be particularly surprising at this point. So let me just write those down. So I have the following theorem. So we'll let phi be a ring homomorphism from a ring R to a ring S. And let's let A be a subring of R. And we'll let B be an ideal in S. Okay, so this is the setup. We have phi going from a ring R to a ring S, and inside of R we have a subring called A, and inside of S we have an ideal B. Okay, then we have the following statements. So first, for any little r inside of your ring R and integer n, we have that phi of r to the n is equal to phi of r to the n. Second, we have the set phi of A. So this is just phi applied to every element of A. This is a subring in S. Three, under what conditions is this thing an ideal? So if A is an ideal, and phi is surjective, then phi of A is an ideal. So you can maybe think about or wonder why we need this condition that phi is surjective. A fourth one, phi inverse of B. So this is the set of all R's that map to B. So the R's in R such that phi of R is an element of B. This is an ideal in R. The fifth one, so now this is sort of moving into like properties of the ring that are preserved by homomorphisms. So if R is commutative, then phi of R is commutative. I think here you might ask for an example where S is not commutative, but phi of R is commutative. So that's something you might wonder about with this why we don't get that all of S is commutative. 6, if R has a unity, let's call it 1, and S is not just the 0 ring, and phi is surjective, then phi of 1 is the unity in S. Seven, let's rephrase this. So phi is an isomorphism if and only if the kernel of phi is just the set containing 0. So where I didn't really define this for ring homomorphisms, but maybe you can infer from what we studied about groups. Kernel of phi is those elements R in R that are mapped to 0. And then last, we have that if phi is an isomorphism, then there is something called phi inverse, which gives an isomorphism in the other direction. Okay, so we are not going to go over the proofs of these, but I will give you a few minutes to discuss them. Is there a question? I want that S is not the 0 ring, thanks. Good, okay, are there other questions about these statements? Okay, so I'm gonna give you a few minutes to prove these. A lot of them you can prove just from the analogous statements for groups, and by observing that your ring is a group with respect to addition. So a lot of these will follow from the properties that we already have. So I'll just give you a few minutes to think about those, and then we will get into some analogs of the first isomorphism theorem. Okay, so let's now go into proving something like an analog of the first isomorphism theorem for groups. So before we do that, first, I'm just going to prove that the kernel is an ideal. So we have a theorem that says, so we'll let phi be a homomorphism from R to S, then the kernel of phi is an ideal of R. Okay, so what are we going to use this for? In the rest of the lecture, we're going to look at R mod the kernel of phi and see what this is isomorphic to. But in order to create the this quotient ring, recall that we need to know that the kernel of phi is an ideal, because otherwise the multiplication will not be well defined in this ring. So let's prove that the kernel is an ideal. So what do we need to show that the kernel is an ideal? Yeah.
Show that for all n in R, n times any value of phi should be equal to 5.
Yeah, so we need to show that it has this ideal property that for elements R in R, and let's say A in the kernel, R times A is also in the kernel. And then I guess we also would need to show that it is a subring. So what do we need to show in order to prove that it's a subring? Yeah. Yeah, so we had this like subring test, so we would need to show that it's closed under subtraction. And closed under multiplication. Okay, so let's start with, I guess, the first part. So given an R in the ring and an A in the kernel, let's see why R times A is in the kernel of phi. So the kernel of phi is, this is those elements R in R such that phi of R is equal to 0. So let's apply phi to R times A and see what happens. So phi of R times A, well, our phi preserves the operation, so we can take phi R, so this is equal to phi R times phi A, right? And then A was an element of the kernel, so this is equal to phi R times 0, which is then 0. So this shows that R times A is also in the kernel of phi. Other questions? Okay, so now let's show that it's a subring. And let me go for this second one first. So I claim that we've already proved this. So why is that? We just showed that it's an ideal, so if I take any R in the ring and any A in the kernel, then R times A is in the kernel. To show that it's closed under multiplication, I would do the same thing except for instead of taking R in R, I would take R to be an element of the kernel of phi, right? So what I just proved up here is already a more general statement of phi being closed under multiplication. Does that make sense? Do you all agree? Okay, so we don't need to prove this part. So let's prove that it's closed under subtraction to finish this. So let's let A and B be elements of the kernel. Then we need to show that A minus B is in the kernel. So let's look at phi of A minus B. Okay, well, phi is preserves the operations. So we have this is equal to phi of A minus phi of B. And phi of A and phi of B are each both 0. So this is 0 minus 0, which is 0. So that shows that A minus B is in the kernel of phi as well. Okay, are there questions about this? Yeah.
So we know that homomorphisms preserve the addition operation. How do we know that it's subtraction?
Yeah, okay, so why does it preserve subtraction? So let's say a little more here. Okay, so what is A minus B? This is A plus the additive inverse of B. So this would be equal to phi of A plus phi of minus B. And then we proved that minus B was equal to minus 1 times B, right? So let's rewrite this. Phi of A plus phi of minus 1 times B. And then since it preserves multiplication, then we have that this is phi of A plus okay, this is getting a little bit interesting actually. So phi of minus 1 times phi of B. We didn't assume that these rings had a unity, so I don't even think I can write this step. Right? Okay, so I guess what is the claim here? The claim is that phi of minus B is equal to minus phi of B. So we need to show that this is the additive inverse of, okay, hold on. So we need to show that this thing is the additive inverse of phi of B, right? So phi of minus B plus phi of B, we would want this to be 0, which we can see that this is true. So this is phi of minus B plus B, which is phi of 0, which is 0, right? Okay, so what did this tell us? This says that this is the additive inverse of this. But this is the additive inverse. So that means that they have to be equal. Okay. There was more, that was unexpected. There was more to show there than I thought. Are there questions about this? Okay, so that completes the proof that the kernel is an ideal. So now we'll get an analog of the first isomorphism theorem, which is also called the first isomorphism theorem. Okay, so let's let phi be a homomorphism from R to S. Then I'm going to make a map called psi from R mod the kernel of phi. So since kernel of phi is an ideal, we know that this thing is a ring. So we know how to add and multiply elements in here. And I'm going to make a homomorphism from R mod kernel of phi to phi of R, given by sending an element. So what are elements of R mod kernel of phi? These are cosets. So we're going to take R plus kernel phi and map this thing to phi of R, which is an element of the right-hand ring. Okay, and the claim is that this thing is an isomorphism. Okay, are there questions about this statement? Okay, then let's prove this. Okay, so what do we need to prove in order to prove that this psi is an isomorphism? Yeah.
Have to prove that it's bijective.
Yeah, so we need bijective. We have to show that it preserves the operations. So I'll write. And we would also need to show that it's well defined. So if I were to take two different ways to represent the same element of R mod the kernel of phi, that if I apply psi to those two things, then I get the same thing back. Okay, but we had the same statement for groups. So a lot of these we already know. So which ones do we already know? So R and S are groups with respect to addition, and we had this statement already for groups, right? So which of these four things do I already know are true, just from the first isomorphism theorem for groups? Yeah. What? Yeah, okay, yeah. So we know all of these ones, and we just need to show the multiplication one. Okay, so why? when we proved the first isomorphism theorems for groups, we would have already checked that this map is well defined, and the presence of a multiplication operation doesn't really change that at all. We also already saw that it's bijective, and that won't change either. And we also saw that this map is a group homomorphism, so it will also still be, it will still preserve the addition operation. Okay, so all we have to show is that it preserves multiplication. Are there questions about that? So let's show that it preserves multiplication. So we need to show that if I apply psi to two elements of R mod kernel, then this breaks up into psi of the first one times psi of the second one. So let's apply psi to R plus kernel phi times S plus kernel phi. Okay, so this is going to be one of those proofs where you have to kind of keep track of where everything lives and what the operations are. So we're applying psi to the product of two elements from R mod kernel phi. Okay, so let's see what this is. We know how to multiply elements of R mod kernel phi, so let's just do that inside of psi. So this turns into R times S plus kernel phi, just by the way the multiplication in R mod kernel phi is defined. Okay, so now I know how to apply psi to a single element of R mod kernel phi. So the definition was given here. So this becomes phi of R times S. We know that phi preserves the operations, so this is phi of R times phi of S. And then now what I'm going to do is to just reverse this map. So I know that phi of R was sent to, the thing that was sent to phi of R was R plus kernel phi. So this means that psi of R plus kernel phi is phi of R, and then over here we got psi of S plus kernel phi. Okay, and that finishes it because we wrote this as the product of phi applied, or psi applied to the two arguments. Okay, are there questions about this? Okay, so let's do an example. So let's consider the map from polynomials with real coefficients to the complex numbers given by, I'm going to send a polynomial f of x in here. I'm going to send that to f of I. And my questions are, what is the kernel? And then what can we conclude based on the theorem that we just saw? And then lastly, no, let's just, I'll leave it there. So what is the kernel and what do you conclude from the theorem? So I'll give you a few minutes to think about that example. Okay, let's discuss this example. So, what is the kernel? Yeah. Yeah, so, okay, yeah, so this is going to be polynomials with a factor of x squared plus 1. So in other words, it's the ideal generated by x squared plus 1. So let's see why. Okay, so if f of x is in the kernel, that means that f of I equals 0. So in other words, I is a root of f. And I claim, and you can check this, that if I is a root of f, then minus I is also a root of f. So you can just check this by hand for any polynomial f. And so what that means is that I can factor out the product. So we can factor out x minus I and x plus I from f. But what is this product? This is exactly x squared plus 1. Okay, so that means that any polynomial that's in the kernel is of the form x squared plus 1 times some other polynomial. Okay, so then what do we conclude from the theorem? So we computed the kernel to be this ideal generated by x squared plus 1. So that tells us that Rx mod x squared plus 1 is isomorphic to, well, it's isomorphic to the image of this map. Which will be all complex numbers, right? So y is aside, y is, so we didn't give this map a name, but let's call it phi. So y is phi of Rx equal to C. So if I take some element of C, a plus bi, what is the polynomial that is sent to that? Yeah.
You have f of x equals bx plus a.
Yeah.
That always gets you a plus bi.
Yeah, so bx plus a is sent to a plus bi. So that means that we do in fact get, this map is surjective, so we get all of the complex numbers, and so we have this isomorphism. Okay, so I'm going to stop there for today, and next class we'll see a little bit more about homomorphisms, and then we'll start diving specifically into polynomials. And by the way, Friday, I'm going to dedicate all of Friday to talking about the term paper. So like what is the assignment, what are some suggested topics. I'll go through an example term paper, and you can bring all of your questions. We'll have time to think through some potential topics. Okay, so see you Wednesday. Hi, nice to meet you.
Yeah. I have a couple questions.
Yeah.
So I'm kind of an algebra nut.
Uh-huh.
I wrote one of my entrance essays about algebra.
Oh, nice.
But yeah, so I have a question about that seventh property that you listed
Yeah.
of the homomorphism. I think you said something along those lines.
Uh-huh.
Like this alone was enough to imply that it was isomorphic. I haven't worked with rings in like a year, but I thought
That
it
might
was,
be a typo. I feel like it should just be injected.
yeah, I thought if you had to have both of these properties for phi to be isomorphic. Also the image being
Yeah.
S.
Yeah, yeah.
Or I might have also just missed,
No, I think that's true because
because I thought like this is injectivity, here's surjectivity, and then together it becomes isomorphism.